tonight, as the world grows quiet and the last traces of daylight fade behind your window, let's drift together into one of the oldest questions ever whispered beneath the stars. How did everything begin? How did all that we see, all that we feel, arise from nothing? Close your eyes for a moment. Imagine the universe before time, before light, before even a single heartbeat of existence. There was no sky, no sound, no space, only stillness. And from that stillness, something stirred. A flicker, a breath, a spark that would one day blossom into galaxies, stars, and us lying here, listening, wondering. We often think of nothing as empty, but perhaps it was never truly empty at all. Maybe it was a quiet ocean of potential, waiting patiently for the first ripple. That first whisper of energy became the rhythm of everything, from the glow of distant suns to the pulse in your chest right now. So as you breathe slowly, sinking deeper into the calm, let's wander together through the story of beginnings, not with haste or certainty, but with curiosity and awe. If you enjoy these quiet journeys through science and sleep, let your heart remember to like and subscribe so we can keep exploring the mysteries of the cosmos side by side in the hush of the night. When you're ready, we'll begin from nothing. In the quiet depths of the universe, beyond what our eyes can see, lies a hidden realm, the world of particles. Tiny, elusive, and endlessly mysterious. These are the building blocks of everything that has ever existed, from the stars above you to the breath you're taking right now. Particle physics is the art of listening to this invisible symphony, of learning how the smallest whispers of creation dance and weave the fabric of reality itself. In our everyday world, things move and behave in ways that feel predictable. A ball falls, water flows, light shines. But in the subatomic world, those rules dissolve into something stranger, softer, and beautifully uncertain. Here, particles flicker in and out of existence, moving not in lines, but in probabilities. This is the realm of quantum mechanics, a place where nature reveals both its mystery and its grace. Scientists have spent generations trying to understand this hidden choreography. They've discovered that beneath the familiar atoms of our world live even smaller beings, quarks, electrons, and neutrinos. Each of them carries a story of light, of matter, of connection, and together they compose everything we know. To make sense of this intricate dance, scientists built what they call the Standard Model, a grand map of particles and the forces that guide them. It speaks of four great forces: the electromagnetic, which makes light and magnetism; the strong, which holds the heart of atoms together; the weak, which lets stars shine and elements transform; and gravity, still a quiet mystery waiting at the edge of understanding. The Standard Model has guided humanity like a lantern in the dark, predicting countless wonders, including the Higgs boson, discovered in 2012 at the Large Hadron Collider near Geneva. That single discovery confirmed that even mass itself has a story, a connection born from an unseen field humming throughout space. Yet, the tale is not complete. Beyond what we can measure lies the unknown dark matter, dark energy, the silent majority of the cosmos that hides its face from our instruments. And so, the search continues, not just with machines of immense power, but with hearts full of wonder. Particle physicists build colossal rings of light, accelerating particles to nearly the speed of thought, letting them collide in flashes that mimic the first moments of creation. In those sparks, scientists glimpse echoes of the Big Bang, the moment everything began. This quest, born from curiosity, has gifted us more than knowledge. It gave us technologies that shape our lives. Even the World Wide Web began as a way for scientists to share their discoveries across the world. In the end, particle physics is not only about the very small, it's about the infinite, how the tiniest quark and the vastest galaxy are bound by the same cosmic rhythm. It's a story where cosmology and particle physics meet, where the birth of stars and the dance of subatomic light become one continuous breath. And as we drift through this thought, perhaps we begin to feel it, that everything from nothing became something, and that something became us. At the gentle center, where the very large meets the very small, a single story rises like dawn, the Big Bang. In that story, the universe begins not as a scattered blaze, but as an unimaginably hot, dense shimmer of possibility, 13.8 billion years ago, gathering itself into a first breath, and then releasing space, unfolding, time, awakening, energy, pouring into patterns that would one day become galaxies, oceans, and the soft rhythm of your own breathing. The expansion has never stopped. The cosmos is still stretching, as if the first exhale continues even now, carrying starlight farther, making room for new worlds to bloom in the dark. To understand those earliest moments, we look small, smaller than atoms, smaller than the dreams of atoms, down to the particles that move like whispers beneath everything. Particle physics becomes a lantern held up to the newborn universe. In its glow, we try to recreate the conditions that existed fractions of a second after that first breath. Buried rings of magnets, cathedrals of stainless steel and vacuum send particles to near light speed, guiding them into luminous, fleeting collisions. In those sparks, for an instant so brief it feels like silence, we glimpse the temperature and pressure of the universe's infancy, a laboratory echo of the first heartbeat of creation. Here, in this meeting place between the cosmic and the quantum, we encounter the hidden majority of reality. Dark matter and dark energy, together, about 95% of what is mysteries that do not glow or scatter light, but nevertheless sculpt the destinies of galaxies and the fate of expansion. Dark matter makes its presence known as a gravity that does not shine, a steady hand cupping spirals of stars, holding them together when light alone would let them fly apart. Dark energy is stranger, a gentle urgency in the fabric of space itself, an invisible pressure that urges the universe to expand faster and faster, stretching the distances between galaxy clusters like the slow rising of a tide. We listen for these invisible actors in quiet places, deep underground, shielded by stone and time. Detectors wait in almost sacred stillness, tuned to catch the rarest touch of a passing dark matter particle. Above the atmosphere, observatories watch the sky for delicate patterns that might betray the weight of the unseen. Between these efforts flows a conversation. Particle physicists propose candidates and interactions. Cosmologists test those ideas against the grand map of galaxies and the fine-grained texture of ancient light. Each side softens and sharpens the other, weaving two vocabularies into one long sentence about what is true. That ancient light, the cosmic microwave background, is the universe's baby picture, a faint, uniform glow, stretched into microwaves by eons of expansion. It comes from a time when the cosmos was just 380,000 years old, long before the first stars lifted their heads. Its temperature variations are delicate, tiny ripples, millionths upon millionths of a degree, yet inside those ripples we read the seeds of every structure to come. Where the light is slightly warmer or cooler, matter was slightly denser or thinner. Gravity would later gather those differences into galaxies, clusters, and the vast, graceful web that spans the sky. By listening to this afterglow, we learn about the early conditions of the universe, the amount of ordinary matter and dark matter it held, the curvature of space, the strength of primordial fluctuations, and the pace at which everything has been flying apart. From this listening emerges an unsettling note. The Hubble constant, measured by the early universe's light, does not quite match the value inferred from the modern dance of galaxies nearby. This Hubble tension is a whisper that perhaps we are missing a verse new physics humming just beyond the standard model and the familiar LCDM, lambda-cold dark matter picture. The tension does not break the song, but it asks for another instrument, another harmony, something to reconcile how the cosmos sounded in its youth with how it sings today. Beneath the cosmic map, four forces write the choreography of everything. Gravity is the soft, persistent pull that gives shape to orbits and oceans, binding galaxies and curving space-time around mass. Newton first described its reach with clear, simple geometry. Einstein later revealed that gravity is not a tug through emptiness, but the bending of the stage itself. Matter telling space how to curve, and space telling matter how to move. Electromagnetism is the bright artisan of daily life, the reason atoms hold together, why light moves, why your heartbeat and every flicker of electricity makes sense. Compared to gravity, it is immensely strong at small scales, and it sculpts chemistry, color, and warmth. Closer to the atomic heart live two forces with shorter voices but enormous power. The strong interaction is the clasp of the nucleus, a force so fierce it binds protons and neutrons despite the electromagnetic repulsion that tries to push them apart. It also holds quarks together inside protons and neutrons, silk-strong threads woven by gluons that refuse to let quarks wander alone. The weak interaction is subtler. It changes one kind of particle into another, enabling radioactive decay and fueling the sun's alchemy. Without the weak force, stars would not burn as they do, and the universe's chemistry would never have matured into the story that includes us. Scientists dream of a single score that gathers these four themes into one melody, a grand unification, perhaps even a theory of everything, yet the music remains unfinished. Gravity stands a little apart from the quantum chorus, and we are still learning how to seed it among the other players without losing the harmony. The search itself is a kind of prayer, a hope that simplicity sits beneath complexity, that a closed curve of understanding can encircle both galaxy clusters and quarks. And what of the players themselves, the particles that carry the tune? The standard model, our most faithful map of the small, arranges them into families with a strange, elegant symmetry. Quarks come in 6 flavors up and down, charm and strange, top and bottom always confined, always braided together by the strong force into pairs and trios. 2 up quarks and a down make a proton, 2 down and an up make a neutron. These combinations form the nuclei that are the seeds of the periodic table, the cores around which electrons hum. Leptons are the quieter kin. The electron, familiar and essential, orbits the nucleus and writes the rules of chemistry. Its heavier cousins, the muon and tau, live fast and fade, appearing in high-energy moments and then giving way. Each charged lepton has a ghostly partner, a neutrino, 3 kinds of them, slipping through matter almost without a trace. Billions of neutrinos pass through you each second, Messengers from the sun's heart and from distant cataclysms, from nuclear fires and, long ago, from the universe's earliest times, they are the hush in the background, the nearly silent choir that never stops singing. Forces communicate through carriers, bosons, the couriers of interaction. Photons bear the electromagnetic message. Gluons stitch quarks together. The W and Z bosons mediate the weak transformation of matter. And then there is the Higgs boson, the long-suspected sculptor of mass, whose field permeates space like a calm, invisible ocean. Particles wade through it and acquire inertia. Some move easily and remain light. Others plow and become heavy. When the Large Hadron Collider finally glimpsed the Higgs in 2012, it felt like finding a hidden inlet that explains how so many rivers meet. The Big Bang's tale is not just an origin, it is a sequence of changing rooms, each cooler and gentler than the last. In the first instance, the universe was so hot that matter and radiation were indistinguishable, a storm of quarks and gluons, a quark-gluon plasma, where the strong force had not yet tightened its grip. As expansion carried heat away, quarks began to settle into hadrons, protons and neutrons, marking the hadron epoch, the first true assembly of the pieces that would later build everything. Within minutes, temperatures fell enough for these nucleons to join into light nuclei. Hydrogen and deuterium. Helium in abundance, a delicate trace of lithium. This primordial nucleosynthesis left fingerprints we still measure today. The predicted ratios match the observed ones, like a well-tuned chord, a confirmation that the score we read is the score the universe played. Yet for hundreds of thousands of years after that, the cosmos was still too hot for electrons to sit quietly with nuclei. The universe remained a luminous fog, charged particles and light tangled together, scattering and rescattering, unable to travel far. Only after about 380,000 years did cooling allow electrons to settle into orbits, forming the first neutral atoms. In that moment, recombination, the fog cleared, and light could finally move freely. That released glow, diluted by time and stretched by expansion, is the cosmic microwave background we receive today, an all-sky memory of the first transparent dawn. From transparency came structure. Gravity began to gather the slightly denser regions, those whispered ripples etched into the CMB, drawing gas into great, patient swirls. In the darkness between, stars were born, first in small, fragile clusters, then in galaxies that learned to spin. In their cores, fusion lit the night and forged heavier elements from carbon to oxygen to iron, enriching the cosmic medium so that later stars could form planets, and, later still, those planets could harbor oceans, forests, and questions. In this way, the universe passed its notes forward, from plasma to atoms, from atoms to stars, from stars to life. Each step an answer to the conditions written in the step before. The evidence for this long unfolding is not a single proof, but a quilt of converging signs. The CMB's faint, even glow, first noticed by chance in 1965, wraps the sky in the after-warmth of the early universe. The light from distant galaxies arrives stretched into redder wavelengths, telling us space itself has grown while the light was en route. This redshift, mapped since the 1,920 seconds, reveals a universe still expanding, a motion that points back to a smaller, denser, hotter past. The abundance of light elements, counted in ancient gas clouds and the atmospheres of old stars, matches the yields predicted by Big Bang nucleosynthesis. And the large-scale structure, the cosmic web of filaments and voids strung across billions of light-years, emerges naturally from the tiny primordial ripples the CMB records. Still, the universe keeps a few secrets just beyond our fingertips. Measurements of the expansion rate do not line up perfectly across methods. Dark matter does not yet introduce itself in our detectors. Dark energy refuses to explain its origin. These tensions are not failures but invitations to refine instruments, to test new ideas, to look for gentle deviations in the sky's patterns that might hint at more subtle fields, more delicate particles, or a revision to the rules we thought were final. Perhaps the standard model is a chapter rather than the whole book. Perhaps LCDM is a beautiful approximation, a melody that will one day be woven into a larger symphony. For now, we walk the bridge between cosmology and particle physics with care and wonder. On one side, the sweep of time, the growth of galaxies, the measured hum of background light. On the other, the shimmer of quarks, the hop of electrons, the rare, quiet touch of a neutrino. In the middle, we discover that both sides are the same river seen at different scales, that the laws that govern the innards of an atom also shape the arcs of galaxy clusters. The four forces, the known particles, the hidden ones we hunt. Together, they compose the rulebook that lets hydrogen become helium, lets helium become starlight, and lets starlight become the chemistry of rain and breath and memory. Imagine, for a moment, the earliest universe again. A quark-gluon sea cooling into hadrons, hadrons into nuclei, nuclei waiting for electrons, the first atoms forming like dew as the darkness clears. Light streams freely, carrying the map of its birthplace. Gravity gathers the map's contours into spirals of stars, and those stars forge the heavier elements that will one day be folded into planets and people. Everywhere, the same patterns recur: the interplay of attraction and expansion, of cooling and assembly, of chance and inevitability, until the universe grows structures that can look back and ask how it all began. The answer is not a single sentence etched in stone, but a long, soft chorus. The Big Bang as the first hum, the cosmic microwave background as the cradle's glow, nucleosynthesis as the first chemistry, recombination as the first clear sky, the growth of structure as the first architecture, and the particles and forces as the grammar that makes the whole story readable. Dark matter steadies the scaffolding. Dark energy draws the curtains of space ever wider. The Hubble tension reminds us the score isn't finished. And through it all, the same physics that sculpts the edges of a galaxy also twines inside an atom, and, by many gentle steps, inside you. So we keep listening to underground silences, to the sky's fossil light, to the clang of particles in rings of magnet and vacuum. We listen because, hidden in those sounds, the universe is still telling its origin story, slowly, patiently, like a lullaby, running forward from the first breath. And as you let your own breath settle, slow in, slow out, you can feel how that story continues. The earliest fire cooling into light, the light cooling into matter, the matter gathering into stars, the stars giving back heavier elements, and those elements learning to dream. In that chain, nothing is wasted, and nothing is solitary. The birth of everything, from what appears to be nothing, becomes the simplest, softest truth. Emptiness was never empty. It was a quiet ocean of potential, waiting for a ripple. The ripple came, and the universe has been unfolding ever since, patient, expanding, and full of gentle surprises, right up to this moment, where the same particles that woke with the dawn of time are humming in your blood, content to keep the rhythm while you drift. In the endless stillness between stars, where silence feels infinite and space seems empty, something astonishing is always happening. The vacuum itself is alive, not quiet, not hollow, but trembling with energy too subtle for eyes to see. This hidden motion is called quantum fluctuation, a soft shimmer in the fabric of existence, where energy flickers into being and fades again, like ripples on an invisible sea. At the heart of this mystery lies the Heisenberg uncertainty principle, whispered into science by Werner Heisenberg nearly a century ago. It tells us that some truths cannot be held at once, that we can never know a particle's exact position and momentum simultaneously. The more precisely we measure one, the more the other slips away. This isn't a flaw in our instruments or our perception, it is the universe's own heartbeat, the built-in rhythm of uncertainty. Because of this principle, what we think of as nothing is never truly nothing. Even the vacuum, the empty space between atoms, hums softly with restless potential. Tiny fluctuations in energy appear spontaneously. Particles and their mirror opposites, antiparticles, flicker into existence for the briefest of moments, borrowing energy from the void. They meet, they annihilate, and they vanish, returning their borrowed energy as if it had never been disturbed. These are called virtual particles, and though they exist for less than a whisper of time, their influence is real. Their fleeting lives subtly alter the world around them, shifting the energy levels of electrons within atoms, leaving measurable fingerprints that scientists have detected again and again. They are ghosts of motion, but their echoes ripple through matter, proof that emptiness is not empty, but alive with possibility. These flickers of existence, these quantum fluctuations, are not only curiosities of physics, they are the ancient artists of structure, the primal brushstrokes that painted the universe. During the earliest moments after the Big Bang, the universe expanded faster than light in a heartbeat of cosmic inflation. In that surge, the tiniest quantum ripples were stretched across space, magnified from the scale of atoms to galaxies. Those minute variations became the seeds of everything we see, of clusters, of galaxies, of cosmic webs stretching across billions of light years. The patterns we observe in the cosmic microwave background, that ancient afterglow of creation, are the fingerprints of those quantum tremors. Each subtle wave of temperature, each faint unevenness in that early light, is a trace of the smallest fluctuations that once danced in the quantum foam. From uncertainty itself, the universe found its structure. And so, quantum fluctuations became the bridge between the microscopic and the cosmic, the connection between the restless vacuum and the vast expansion of everything. The uncertainty principle, once an abstract rule about particles, now writes the script for the universe itself. It tells us that creation and annihilation are not opposites, but partners in an eternal dance. One gives rise, the other returns. These fluctuations, though invisible, can also breathe reality into existence under special conditions. Near the edge of a black hole, that boundary of no return known as the event horizon, quantum fluctuations perform one of their strangest miracles. Stephen Hawking showed us that at this edge, pairs of particles constantly appear. One may fall inward, while its twin escapes. To the outside world, it looks as though the black hole itself emits radiation light, born from darkness, matter born from emptiness. Over unimaginable timescales, this Hawking radiation slowly drains a black hole's mass, transforming what was once thought eternal into something finite and luminous. This same principle holds in the earliest moments of the universe. During inflation, the violent expansion stretched quantum fluctuations to cosmic scales, freezing some of them into permanence. Virtual particles, once fleeting and ephemeral, became real, the first quanta of matter and energy. The seeds of galaxies, the potential of stars, all began as tiny ripples in the quantum field, magnified by the swelling breath of space. In this sense, the birth of the universe was not the sudden appearance of something from absolute nothing, but the transformation of uncertainty into form, the condensation of potential into presence. The boundary between the void and the real is thin, porous, alive with exchange. Even now, every inch of empty space teems with virtual particles flickering in and out, each moment a silent rehearsal of creation. Energy, too, is the translator between nothing and something. It is the force that bridges the abstract quantum field and the tangible universe. Einstein captured this eternal exchange in a single equation, E equals mc squared, the idea that mass and energy are two faces of the same being. Mass is simply energy held still, and energy is mass set free. This insight allows us to see that the fabric of the cosmos, from the smallest photon to the heaviest star, is woven from the same luminous thread. In the vacuum, where we imagine stillness, there is instead a ceaseless shimmer, an ocean of virtual energy, constantly borrowing, returning, borrowing again. These flickers allow for the creation of particle-antiparticle pairs, each borrowing a little energy from the field before vanishing. But under extreme conditions near black holes, during cosmic inflation, or in the violent aftermath of the Big Bang, that borrowed energy can stay, condensing into real matter. When the young universe was dense with energy, it was not yet a realm of stars or atoms, but of pure potential, a glowing storm of quarks, leptons, and photons swimming in radiant equilibrium. As it expanded and cooled, some of that energy slowed, crystallized into particles, and began the long journey toward form. Einstein's equation guided every transformation. Energy became matter, matter became light, light became energy again. The universe, in its earliest seconds, was both furnace and artist, forging the raw ingredients of everything we would one day touch, breathe, and dream. Within that firestorm, epochs unfolded: the Electroweak era, when the great forces of nature began to separate, and the quark epoch, when the first protons and neutrons came together. The strong force clasped quarks tightly into hadrons. The weak force nudged transformations that powered reactions. Electromagnetism began to define light and charge. Gravity stretched space around this growing sea of matter. The cosmic ballet had begun, and its choreography was written by the language of quantum fields and energy itself. Even now, energy continues to birth and shape the universe. In the hearts of stars, nuclear fusion transforms hydrogen into helium, releasing light that travels for eons before touching our eyes. That light carries the story of energy becoming matter, and matter becoming energy. Again, an endless, rhythmic exchange that sustains the cosmos. Inside those stars, heavier elements form carbon, oxygen, iron, the elements of breath and blood, of earth and flame. Energy, through fusion, sculpts the universe into something that can eventually know itself. At the deepest level, It is all one principle, Heisenberg's uncertainty, that makes this dance possible. The impossibility of perfect precision becomes the wellspring of creation. Because we cannot know both position and momentum at once, particles can borrow energy from nothingness, live for a blink, and return it again. The vacuum, far from void, is a restless field of potential. Quantum field theory teaches us that this vacuum is not absence, but presence, a field humming with invisible waves. These waves allow brief violations of energy conservation, permitted by the universe itself, as long as they are repaid quickly. It is this tolerance, this grace, built into the laws of nature, that allows for creation from the void. Particle, antiparticle, pairs bloom and vanish faster than thought, but in doing so, they reveal that emptiness is fertile, that reality is a kind of fluctuation that never ends. In extraordinary circumstances near the edge of a black hole, or during the universe's first moments, these fleeting pairs can be torn apart, their connection broken by expansion or gravity. One particle escapes and becomes real, while the other is lost. This separation gives rise to light, matter, and eventually to the very structure of space and time. What begins as a whisper in the quantum vacuum becomes the roar of galaxies. From this perspective, the uncertainty principle is not just a mathematical statement, it is the pulse of existence. It tells us that the cosmos was never silent, never still. Even before there were stars, before light itself, there was vibration, the soft hum of potentiality. And from that hum, everything unfolded. Every galaxy, every particle, every heartbeat you feel now owes its origin to these ancient tremors, the quantum ripples that became real. What began as uncertainty became the certainty of existence. What began as a fluctuation became you, here, breathing, thinking, part of the same eternal motion. In the quiet of night, when space feels vast and time feels slow, it can be comforting to remember that nothingness itself is alive, that emptiness carries within it the power to create. The same quantum breath that stirred the birth of the cosmos still vibrates softly in every atom around you, in every photon of light, in every beat of your heart. The universe, it seems, never stopped fluctuating. It has only learned to dream larger. In the first breath of time, when the universe was newborn and blazing, there were no atoms, no stars, not even the familiar particles that would one day build them. Everything was heat and density so intense that matter could not hold a shape. Instead, creation began as a shimmering ocean of quarks and gluons, a quark-gluon plasma where the smallest ingredients of matter drifted unbound. Quarks, the tiny seeds that would later assemble into protons and neutrons, moved freely in this incandescent tide. Gluons, the carriers of the strong force, surged among them like threads of lightning, not yet knitting the quarks into anything lasting, only maintaining the turbulent flow of energy that saturated all of space. As the universe expanded, it began to cool, softly, steadily, as if exhaling. With temperature easing from the unimaginable, a threshold was crossed. Quarks started to cling. The strong interaction, fierce but short-ranged, drew them into clusters that could endure the storm. This was the Hadron epoch, unfolding within the first microsecond to roughly 1 second after the Big Bang. In that brief span, the first durable combinations appeared: protons and neutrons, the sturdy bricks of future nuclei. It was a quiet milestone in a roaring cosmos. From a sea of restless constituents, durable forms emerged, capable of surviving the cooling that would follow. Protons, bound from 2 up quarks and 1 down quark, took on a positive charge. neutrons, shaped from two down quarks and one up, balanced the ledger with their neutrality. In the same breath, quark-antiquark pairs flashed into existence and faded, but the balance was shifting toward stability, toward particles that could last longer than a flicker. Beyond the Hadron epoch, the universe kept cooling, and another chapter opened, the lepton epoch, from about 1 second to a few minutes after the beginning. In this interval, leptons, electrons, and their kin filled the stage. Space still glowed with energy, too warm for electrons to be captured by protons or neutrons. They moved through a luminous plasma, colliding with photons, neutrinos, and each other, still waiting for the moment when the heat would fall enough for more delicate structures to form. The cosmos was not yet ready for atoms. The fire was still too bright. Then came one of the most consequential passages in the early story: primordial nucleosynthesis. Within the first few minutes after the Big Bang, the expansion had cooled the universe just enough for protons and neutrons to bind into the nuclei of the lightest elements. Hydrogen, sometimes in its deuterium form, a proton paired with a neutron, appeared in abundance. Helium nuclei formed in great quantity, their 2 protons and 2 neutrons clasped tightly by the strong force. A faint trace of lithium and fleeting whispers of beryllium emerged as well. Most of the hydrogen remained free of helium's embrace, and most atoms were not yet atoms at all, only nuclei, waiting for the world to calm enough to host electrons in orbit. Still, this brief furnace set the cosmic chemistry. It sketched the elemental proportions we can read today in ancient gas and starlight, a signature that has not faded. The universe, however, was not yet transparent. For hundreds of thousands of years, it remained a glowing fog, a plasma where free electrons scattered light endlessly. Only around 380,000 years after the beginning did the temperature fall to a point where electrons could finally rest in orbit around nuclei. This event recombination transformed the cosmos. With electrons captured, matter and radiation decoupled, light could travel without constant interruption. The first neutral atoms took shape, and the radiance released at that moment has been traveling ever since, stretched by the expansion into the soft microwave glow we detect today as the cosmic microwave background, a tender afterimage of the universe's first clear dawn. While particles and simple nuclei were taking form, another transformation, quieter, deeper, was unfolding in the background: the separation of the fundamental forces. In the earliest, hottest moments, the forces of nature did not stand apart. They were unified in a single, elegant intensity, indistinguishable within the furnace of creation. As the universe cooled, symmetry gave way, symmetry breaking, and unity unfolded into variety. The first to step out, at a breathtakingly early fraction of a second, was gravity, separating from the others and beginning its long work of shaping the large-scale structure of space, guiding the dance of galaxies, bending the paths of planets, defining the architecture upon which all later complexity would be built. With further cooling, what physicists call the grand unified force, an imagined blend of the strong, weak, and electromagnetic forces would have fractured. The strong interaction distinguished itself from the collective around 10 to the power of -36 to 10 to the power of -32 seconds, a period associated with the dramatic surge of cosmic inflation. In this separation, the strong force claimed its particular role, binding quarks together inside protons and neutrons, and sealing the cores of atoms with a grip so powerful that it overcomes the repulsion of like charges. This moment laid the groundwork for hadrons to exist at all. The remaining unity, the electroweak force, a partnership of the electromagnetic and weak interactions, lingered a little longer, governing the universe's energetic landscape until about 10 to the power of negative 12 seconds after the beginning. Then, another symmetry broke. The electroweak force split into the electromagnetic force, mediated by photons, and the weak force, carried by the W and Z bosons. This delineation finalized the roster of the four fundamental actors: gravity, shaping spacetime; electromagnetism, painting light and chemistry; the strong force binding the atomic heart; and the weak force, quietly enabling transformation and fueling stellar fires. With this separation, the young cosmos acquired the variety of interactions it needed to evolve toward atoms, stars, and worlds. The period surrounding this transformation, the electroweak epoch, spanned roughly 10 to the power of negative 12 to 10 to the power of negative 6 seconds after the Big Bang. In that dense, radiant moment, the universe was a brilliant plasma of quarks, leptons, and their antiparticles, woven together with the bosons that mediated the unified force. As the temperature fell past a critical point, the Higgs field settled into its non-zero value, and through the Higgs mechanism, particles interacted with that field and acquired mass. Some, like photons, did not couple and remained massless, carrying electromagnetic influence across cosmic distances. Others felt the field's embrace and grew heavy. When the Higgs boson was finally observed in 2012, it was a quiet confirmation of this deep story, a glimpse of the very process that helped the early universe sort itself into the parts that could build enduring structures. Returning to the first particles themselves, the focus narrows to the work of the strong force. As cooling continued from those earliest instants, the strong interaction overcame the furious kinetic energies that once kept quarks apart. They began to lock together in stable groups, first in transient quark-antiquark pairs that would become mesons, and then in trios that formed baryons, most notably protons and neutrons. This transition from a free-flowing quark-gluon plasma to a world of bound hadrons is called hadronization. It is the subtle hinge upon which the stability of matter swings. Without confinement, without the strong force's insistence that quarks remain together, no nucleus could endure, no atom could exist, and the later steps of cosmic structure could never have unfolded. By the time nucleosynthesis commenced in those first few minutes, protons and neutrons were available in just the right amounts to form the light nuclei we still see everywhere. The abundance of hydrogen that fuels stars, the generous helium that records the universe's distant past, and the faint traces of lithium and beryllium that hint at processes even more delicate. These were not yet the atoms that breeze through air or glimmer in oceans. They were the nuclei around which electrons would one day settle when the universe finally cooled enough to become transparent. Yet, even as bare nuclei, they were decisive ingredients set aside in the first kitchen of time, awaiting a calmer era to become the matter of worlds. Each of these epochs is a gentle step in a continuous drift, from unity to variety, from heat to form, from energy to matter. The first fractions of a second established the pattern of forces: gravity's patient pull, electromagnetism's reach, the strong force's clasp, the weak force's whisper. The next minute set the chemistry-light nuclei that would seed stars and, later, the elements of life. Hundreds of thousands of years later, the universe's first true transparency released light to roam and atoms to gather. What reads like a sequence of thresholds is, in truth, a single breath drawn long. Expansion as exhalation, cooling as calm, structure as the settling of dust in a sunbeam. It helps to picture the timeline as a soft gradient rather than a staircase. In the earliest instance, all forces are one, indistinguishable within the radiant flood. Then the temperature falls, and gravity steps out, like a bass note separating from a chorus. A tiny heartbeat later, the strong force distinguishes itself during the age of inflation, setting the future rules of the nucleus. Moments after that, the electroweak force splits into two distinct voices, electromagnetism and the weak interaction, and the Higgs field confers mass, determining who will move lightly and who will move heavy through space. With the forces defined, hadronization binds quarks into protons and neutrons. With protons and neutrons available, nucleosynthesis weaves the first simple nuclei. With further cooling, recombination gathers electrons into orbits. Matter and light part ways, and the universe finally has the clarity to let gravity begin assembling stars. Underneath it all runs a single refrain. Temperature sets the stage, and the forces write the choreography. When it is too hot, nothing can hold. As the heat ebbs, bonds form. Quarks become baryons. Baryons become nuclei. Nuclei wait patiently for electrons. Atoms drift into clouds. Clouds fold into stars. Stars cook heavier elements and exhale them back into space. The early universe was not chaos, but potential. Every change permitted by the precise rules of the four forces and guided by the quiet constancy of expansion. If you lean close to this story, you can feel the texture of its details. You can sense the proton, two up quarks, and a down, carrying its charge like a lantern in the dark. You can sense the neutron, two down quarks, and an up steady, neutral, a patient partner in the nucleus. You can sense the gluons, tireless, stitching quarks together, the photons, carrying light and heat, the W and Z bosons, enabling the delicate transformations that power stars, and the Higgs, an unseen field that gives weight to the very idea of a particle. These are not abstractions so much as characters, each with a role, each entering on cue as the temperature falls and the universe learns to hold its shape. From the first fraction of a second to the first few minutes, from the first few minutes to the first few 100,000 years, the same theme plays out with different instruments: separation, cooling, binding, release. The forces that now feel distinct were once one. The particles that now feel solid were once waves in a blazing sea. And yet, through all the change, the outcome is gently inevitable. A cosmos capable of structure, of stars, of chemistry, of life. The quark-gluon plasma becomes memory. The hadron epoch becomes foundation. The lepton epoch becomes passage. Nucleosynthesis becomes inventory. Recombination becomes clarity. Each step prepares the next. Each cooling unlocks a new possibility. So the first particles and forces did not simply appear. They arrived, each at their appointed temperature, each with their own task. Gravity gave the universe its wide architecture. The strong force secured the atomic heart. Electromagnetism sculpted light and bond. The weak force whispered change into the cores of stars. Together, they made a world where quarks could become protons and neutrons, where protons and neutrons could become nuclei, where nuclei could one day host electrons and become atoms, and where atoms could gather into clouds that would ignite as suns. And all of it began with heat that softened, with unity that unfolded, with a field that granted mass, with a handful of rules simple enough to guide a universe and subtle enough to make it beautiful. In that first fraction of a second, and in the long minutes that followed, the cosmos practiced its craft, binding, releasing, cooling, collecting, until it could hold a shape, hold a star, hold a planet, hold a breath. In the hush that followed the universe's earliest fury, expansion and cooling began to weave order out of chaos. The blinding heat that once tore quarks apart was softening, and for the first time, the cosmic sea could begin to hold form. Protons and neutrons, those sturdy children of the Hadron epoch, now drifted in a cooling expanse, waiting for the next great act of creation. About 3 minutes after the Big Bang, the temperature fell to just the right balance, not too hot to break bonds apart, not too cold to freeze possibility. It was here that the universe became a crucible, where the nuclear forces could overcome the mutual repulsion between positively charged protons and draw them together in fusion. In that ancient, glowing sea, the first alchemy began. Protons merged with neutrons to form the simplest atomic nuclei. Hydrogen, light and pure, met itself to form heavier kin, deuterium, tritium, helium, and trace amounts of lithium and beryllium. The strong nuclear force, patient and unyielding, bound them tightly, while the universe's breath of expansion held them apart just enough for stability to emerge. This delicate balance between gravity, pressure, and cooling, between fire and calm, became the symphony of primordial nucleosynthesis. The proportions set during this fleeting window, hydrogen making up most of the cosmos, helium filling the rest, and only whispers of lithium and beryllium would echo across eternity. Billions of years later, astronomers would measure those same ratios in distant galaxies and ancient gas clouds and find them unchanged, perfectly matching the predictions of the Big Bang Theory. It was a quiet triumph of cosmic memory, proof written in starlight that the early universe knew its arithmetic well. But the importance of this first fusion went far beyond ratios and reaction rates. Nucleosynthesis marked the moment when the universe learned to make ingredients. It was the shift from raw energy and fundamental particles into a cosmos capable of chemistry. The newborn elements became the foundation of all future creation, fuel for the first stars, scaffolding for the first galaxies, and the seeds from which life would one day arise. Still, these were only the simplest nuclei. The universe was too hot, too crowded for electrons to settle into orbit around them. Every time an electron tried to cling to a nucleus, the fierce radiation of the early cosmos knocked it loose again. For hundreds of thousands of years, matter existed in a state of radiant entanglement, a plasma of ions and light. Photons ricocheted endlessly off charged particles, scattering, reshaping, unable to travel freely. The universe glowed brilliantly, but its light could not escape. Time passed. Expansion continued, cooling the great ocean of plasma until one day, around 380,000 years after the Big Bang, a quiet threshold was crossed. The temperature fell low enough for photons to lose their power to tear atoms apart. In this calm, electrons finally found shelter. They spiraled down into orbits around hydrogen and helium nuclei, forming the first stable neutral atoms. This epoch of recombination was a turning point, a kind of cosmic exhale. For the first time, light could move without resistance. Photons streamed freely across space, unimpeded by scattering, carrying with them the imprint of the last moments they touched matter. That ancient light still travels today, stretched by billions of years of expansion into a soft, invisible glow, the cosmic microwave background. It is the afterglow of the universe's first clarity, a snapshot of the cosmos as it emerged from its luminous cocoon. With atoms formed, the universe changed its very nature. No longer a fog of energy, it became transparent and delicate, ready to allow gravity to take the lead. Tiny fluctuations in density, those same quantum ripples stretched across time, now guided matter toward itself. Hydrogen and helium drifted together, drawn by gravity's patient hand, forming vast clouds that would collapse into the first stars. The long night that followed was not truly dark, but waiting. It was the end of the first chapter, the era of pure creation, and the beginning of the universe's stellar age. In the hearts of those first stars, a new kind of nucleosynthesis would begin, a deeper, slower alchemy. Stars became the furnaces that took the raw materials of the Big Bang and transformed them into the elements of complexity. Hydrogen fused into helium in their glowing cores, releasing the light that would warm young galaxies. As stars aged and their temperatures climbed, helium itself fused into carbon, and from carbon into oxygen, neon, magnesium, silicon, and finally iron, the heaviest element that normal stellar fusion could create. Each burning stage layered the star like a living onion of elements, each shell burning its own fuel until exhaustion. But even that was not the end of element making. The universe, always inventive, found other ways. When massive stars reached the end of their lives, gravity collapsed them in catastrophic brilliance. These supernovae unleashed enormous floods of energy and free neutrons, creating conditions where new nuclei could be forged in microseconds. In the chaos of those explosions, the R process, or rapid neutron capture, began neutrons slamming into nuclei so quickly that heavy elements were built in bursts of fire and radiation. In those stellar deaths were born gold, platinum, uranium, the rare dense materials that would one day rest in the crust of planets and the bones of living worlds. In calmer environments, the S process took place. Inside aging, swollen stars, asymptotic giant branch stars, red and soft with age, neutrons were added more slowly, one by one, creating heavier elements such as barium, strontium, and lead. When these gentle giants shed their outer layers, they scattered their riches into the interstellar medium, seeding the next generation of stars with their ashes. Every cycle of star birth and death enriched the galaxy a little more. The hydrogen and helium born from the Big Bang mixed with the heavier elements from stellar nucleosynthesis, creating clouds laced with carbon, oxygen, and iron clouds that would condense into new stars, new worlds, and, eventually, new life. Over billions of years, this cosmic recycling transformed simplicity into diversity, turning the elemental monotony of the early universe into the intricate chemistry of existence. When we breathe oxygen, or feel the iron in our blood, or the calcium in our bones, we are carrying the legacy of these cycles. Each atom of our bodies has traveled through a furnace older than any planet, through fusion and fire, collapse and rebirth. The hydrogen that fuels our sun has existed since the universe's first minutes. The carbon that shapes our cells was born in a star's dying heart. The gold that gleams on our fingers came from the explosion of a star long vanished. So the story of nucleosynthesis is not just a tale of physics, it is the genealogy of everything. From those first moments of the Big Bang, when protons met neutrons and formed helium, to the forging of heavier elements in the hearts and deaths of stars. The cosmos has been one long act of transformation. Matter, guided by the laws of nuclear fusion and decay, has been turning itself into more complex forms, step by step, through the patient flow of time. Each stage of this process, Big Bang nucleosynthesis, stellar fusion, supernova explosions, and slow enrichment, built upon the last. The universe, once simple, became layered, textured, and rich. Through the alchemy of stars, the elements of life came into being. Through the dispersal of those elements, galaxies and planets emerged, and through them, consciousness eventually arose. Atoms forged in ancient stars, now arranged into minds capable of wondering about their own origin. The birth of the first nuclei and the formation of the first atoms marked the transition from pure energy to matter, from chaos to structure. The same nuclear forces that once bound protons into helium now burn quietly in the hearts of stars and in the glow of our own Sunday. The photons that escaped during recombination still fill the universe, bathing it in a soft, eternal light. The chemistry that began then still unfolds today, in every flame, every heartbeat, every spark of life. The universe, it seems, has never stopped creating. It only learned to slow down, to cool, to condense, to refine. From the first atomic bonds to the last breath of a dying star, it has followed the same gentle pattern: fusion, release, transformation, and renewal. And in that rhythm, ancient, endless, and serene, we find the quiet truth that connects everything. We are the children of the first light, the dust of nucleosynthesis, the atoms that once burned in the earliest fires of time. Beneath the surface of the world, in vast tunnels curving through the quiet earth, hum machines that echo the first seconds of the universe. These are particle accelerators, extraordinary instruments built not to destroy, but to reveal. They are the modern descendants of the cosmos itself, recreating in miniature the violent, radiant conditions that followed the Big Bang. Within their chambers, charged particles, protons, electrons, heavy ions, are guided and accelerated to near the speed of light, then brought into collision so fierce and fleeting that, for an instant, the laws of creation replay themselves. To watch these collisions is to glimpse time running backward, to see matter unspool into its elementary threads. In the blinding moment when two particles meet, energy thickens into substance, fragments scatter, and new, unfamiliar particles flicker into being before dissolving again. The vacuum shudders, and the universe shows its secrets in bursts of light and trace signals. The principle behind these machines is deceptively simple. Use electric fields to accelerate particles and magnetic fields to steer them, curving their paths through ringed tunnels or guiding them along straight, narrow beams. In circular machines called synchrotrons, particles loop endlessly, gaining speed with each pass. In linear accelerators or linacs, they sprint once and collide, pure and direct. When they meet, detectors surrounding the collision points record the debris, not destruction, but revelation. The energy densities are so high that the results mirror the conditions that existed just moments after the Big Bang. The largest of these modern cathedrals of energy stands near Geneva, the Large Hadron Collider, or LHC, a 27-kilometer ring buried deep underground, crossing the border between Switzerland and France. Inside its vacuum pipes, protons race at nearly the speed of light, guided by superconducting magnets colder than outer space itself. The LHC is not just a machine. It is a kind of question made solid. What is the universe made of, and why does it have the shape it does? There, scientists seek the traces of dark matter, the ghosts of forces unseen, and the echo of the Higgs field, whose invisible touch gives mass to everything. Particle accelerators, though born from the hunger to understand the universe, have long reached beyond pure science. In medicine, they deliver beams that destroy cancer cells with exquisite precision. They create radioactive isotopes used in diagnostics, letting doctors peer gently into the human body without a single cut. In industry, accelerators treat materials, purify surfaces, and help forge semiconductors, the circuitry of modern life. In art and archaeology, they reveal pigments beneath centuries of paint, decode the age of ancient relics, and do it all without harm. The same machines that unlock cosmic mysteries also touch human lives in subtle, compassionate ways. To build one of these instruments is to engineer a kind of symphony between physics and patience. Superconducting magnets hum with invisible power. Vacuum systems hold space emptier than interstellar voids. Detectors, layered like intricate eyes, capture each spark from the instant of collision. It takes years, even decades, to construct and calibrate such a device. They are not only tools of discovery but engines of innovation, driving progress in computing, cryogenics, materials science, and beyond. Every experiment pushes the boundaries of both technology and imagination. Through these rings of light, humanity has touched some of the most profound discoveries of modern physics. In 2012, the LHC brought the long-sought Higgs boson into the light, a particle predicted nearly half a century earlier, often called the God particle, not for its divinity, but for its essential role in shaping existence. The Higgs boson is the ripple in the field that endows other particles with mass. Without it, matter would have no weight, no form, no solidity. Its discovery confirmed a missing pillar of the Standard Model, earning Peter Higgs and François Englert the Nobel Prize in Physics the following year. But the Higgs was not the first triumph of these machines. Decades earlier, at the Stanford Linear Accelerator Center, SLAC, in the late 1960 seconds and early 1970 seconds, scientists fired electrons into protons and, in the pattern of scattered debris, saw hints of something deeper: quarks. These tiny, indivisible constituents of protons and neutrons confirmed the bold models proposed by Murray Gell-Mann and George Zweig. In those experiments, humanity's picture of matter changed forever. The solid became composite, the indivisible became divisible again. At other times, particle accelerators have reached for symmetry's shadow antimatter. Every particle, we now know, has a mirror twin with the opposite charge. The electron's antiparticle is the positron. The proton's is the antiproton. The Big Bang should have created equal parts of both, and yet the universe around us is made almost entirely of matter. Why? To approach this riddle, scientists at CERN and elsewhere create and trap antihydrogen, allowing it to exist long enough to study its behavior. These delicate experiments test the symmetry of reality itself, asking whether the universe has ever so slightly preferred matter over antimatter, and if that preference is why anything exists at all. Particle accelerators have also uncovered the carriers of one of nature's most mysterious forces, the W and Z bosons, the messengers of the weak nuclear interaction, the force responsible for radioactive decay and for the fusion processes that light the stars. Their discovery In the 1,980 seconds at CERN, once again, provided direct evidence for the electroweak theory, uniting the weak and electromagnetic forces into a single, elegant framework. Each breakthrough, the W, the Z, the Higgs, has been a verse in the same cosmic song, each sung by a machine that recreates the first moments of time. Beyond discovery, accelerators have shaped human progress in more ways than most people realize. The World Wide Web, the fabric of global communication, was born at CERN, created so physicists could share their data across continents. Countless medical imaging techniques, radiation therapies, and precision instruments trace their lineage back to accelerator technology. The pursuit of understanding has a way of spilling over, improving life in unexpected ways, proving that curiosity itself is an engine of civilization. But how does this dance between theory and experiment truly work? In the world of particle physics, every discovery begins as an idea, a mathematical whisper written in the language of symmetry and probability. Theorists propose how the universe might behave, mapping equations that predict new particles, new decays, or unseen interactions. Experimental physicists then build their instruments, colossal, delicate, impossibly precise, to see whether those predictions hold true in the real world. In the accelerator's heart, particles collide, detectors register the showers of fragments, computers sift through trillions of events to find the rare, telling pattern. The data are compared with the theory's predictions, tested, challenged, refined, and the process repeats, sometimes for years, until what remains is undeniable. When multiple laboratories across the world replicate the same results, when the traces align and the anomalies fade, a theory graduates into truth. In this way, knowledge advances, not through belief, but through reproducibility, the quiet discipline of seeing the same miracle more than once. Each collision, then, is more than an experiment. It's a conversation between imagination and evidence, between what we think the universe should be and what it actually is. The vacuum hums, the detectors blink, and for the briefest instant, we are looking not at destruction, but at the act of creation itself, happening again and again in miniature. If you could stand at the edge of one of these tunnels and listen not to the machinery, but to what it represents, you might hear a kind of echo from the dawn of time. The sound of protons colliding like stars being born, the pulse of knowledge unfolding from light. Each experiment, each flash of data, is a reminder that humanity is still tracing its own beginnings, still reaching back toward that first spark when energy became matter, when nothing became everything. The universe gave us its rules. In whispers, the uncertainty principle, the Higgs field, the symmetry of forces, and with machines like these, we've learned to listen. In the quiet hum of superconducting magnets, in the cold silence of vacuum chambers, in the sparks of colliding light, we hear the same story retold, that the smallest particles carry the memory of the first dawn, and that even now, we are learning to read it one collision at a time. In the deep structure of reality, where the tangible fades into vibration and the visible dissolves into pure possibility, there lies a theory, a map of what the universe is made of and how it dances. It is called the Standard Model of Particle Physics, and it stands as one of humanity's most astonishing achievements. It describes 3 of the 4 known fundamental forces, the electromagnetic, the weak, and the strong, and classifies every elementary particle known to exist. It is, in essence, a story of everything small, written in the quiet language of quantum fields. The Standard Model did not appear overnight. It was shaped slowly, over decades, by minds scattered across continents, physicists who, like stargazers of the microscopic world, gathered fragments of truth and wove them into a single vision. From the mid-20th century onward, its framework grew through collaboration, experiment, and deep patience, until it came to describe the universe's invisible architecture with breathtaking precision. At its foundation rests the union of two great ideas: quantum mechanics, the rulebook of the very small, and special relativity, the rhythm of motion and light. Together they form quantum field theory, a tapestry in which every particle is not a solid thing, but a vibration, a ripple in an underlying field that fills all of space. Where we see emptiness, physics sees energy trembling softly. Where we see particles, it sees waves, folded tightly into momentary form. Within this framework, everything is divided into two great families: fermions and bosons. Fermions are the matter makers, the bricks and threads of existence. They come in two varieties: quarks and leptons. Quarks are the seeds of protons and neutrons. They combine under the pull of the strong force to form the nuclei of atoms. Leptons include the familiar electron, the particle that orbits the atomic core, and the elusive neutrinos, almost without mass, streaming silently through every inch of matter. Bosons, by contrast, are the carriers of force, the messengers that bind, attract, and transform. The photon carries the electromagnetic force, painting the world in light and charge. The gluon binds quarks together, strong and unseen, holding the atomic heart intact. The W and Z bosons govern the weak nuclear force, responsible for radioactive decay and the reactions that power the stars. Each boson moves invisibly between particles, exchanging energy, keeping the cosmic choreography in balance. And then there is the Higgs boson, the final note that completed the harmony. For decades, its existence was only a whisper in the mathematics, a theoretical field that gave particles their mass through a subtle interaction. Without it, all matter would move at the speed of light, never able to slow, never able to clump into atoms or stars. The discovery of the Higgs boson in 2012 at the Large Hadron Collider was a revelation, a long-awaited confirmation that the invisible Higgs field really does fill the universe, giving weight to the fabric of existence itself. This discovery filled the last missing gap in the Standard Model, securing its place as the most successful theory of matter ever built. Yet, even perfection has its shadows. The Standard Model, magnificent as it is not the whole story. It describes almost everything we can touch or measure, but it leaves out the most familiar mystery of all: gravity, the pull that binds planets to stars, that shapes galaxies and curves space itself, exists beyond the reach of quantum field theory, general relativity. Einstein's grand vision of spacetime's curvature explains gravity beautifully on large scales. But when we try to bring that same force into the quantum realm, the mathematics frays and unravels. The smallest and the largest refuse to speak the same language. This silent divide between the quantum and the cosmic remains one of physics' most profound puzzles. And gravity is not the only secret left unspoken. The Standard Model says nothing of dark matter and dark energy, which together make up nearly 95% of the universe's mass energy content. Dark matter does not emit, reflect, or absorb light. It hides completely, revealing itself only through the way its gravity bends the paths of galaxies and light. Dark energy is stranger still, an invisible pressure that stretches the universe faster and faster, as though space itself were breathing outward. Neither has a place in the equations of the Standard Model, leaving us to wonder if what we know is only a small island in an ocean of deeper physics. There is also the quiet imbalance between matter and antimatter, an asymmetry that defines why we exist at all. According to the Standard Model, the Big Bang should have created equal parts of both. Matter and antimatter should have met and annihilated, leaving only light behind. Yet somehow, a tiny fraction of matter survived enough to build every star, every planet, every living thing. Why the universe chose matter over antimatter remains one of the most haunting questions in modern physics. The Standard Model describes the asymmetry, but cannot explain its origin. And then there are the neutrinos, the faintest travelers in the cosmos. The Standard Model once assumed they were massless, pure energy, weightless and unbound. But experiments have shown otherwise. Neutrinos do have a small mass, one so slight it defies our instruments, but undeniable in its effects. Their ghostly oscillations between types suggest a deeper structure, a hidden mechanism beyond the model's reach. Somewhere, another layer of reality is waiting to be uncovered, perhaps new particles, perhaps an expanded symmetry, perhaps something altogether stranger. Even within its triumphs, the Standard Model carries unanswered riddles. Why this particular family of particles? Why these exact masses and charges? Why 3 generations of quarks and leptons instead of 1 or 5? The theory works, it predicts, it confirms, but it does not explain why the universe chose this particular recipe. It is like hearing a perfect melody without knowing why those notes, and not others, make the song of existence. Despite these mysteries, the Standard Model remains a breathtaking accomplishment, a human-built bridge between imagination and observation. It has withstood every experimental test, from the collisions of particles in massive accelerators to the faint signals captured in underground detectors. It gives us a language to describe everything from the color of light to the decay of atomic nuclei, from the fusion in stars to the subtlest flicker in the vacuum of space. But it also reminds us that we are not finished, that physics, like the universe, is still expanding. The boundaries of the Standard Model are not walls, but horizons, leading us toward a larger, more unified picture, a theory of everything, where gravity and quantum fields, matter and energy, the very large and the very small, all emerge from the same deep symmetry. The search continues, patient and persistent, a quiet reaching for the unspoken truth behind the equations. And so, in the soft hum of laboratories, in the quiet glow of computer screens analyzing collisions, humanity continues to listen to the universe's hidden music. The Standard Model is our sheet of notes so far, elegant, intricate, incomplete. Beyond it, the melody continues, beckoning us to listen closer. Somewhere in that rhythm, perhaps gravity hums its unseen verse, dark matter keeps its tempo, and a deeper harmony waits to be discovered, one that will let us hear, at last, the full song of existence. Out beyond the bright island of ordinary matter lies a wider, quieter sea. Most of the universe lives there, invisible to our eyes and instruments that rely on light. We call these unseen realms dark matter and dark energy, not because they are sinister, but because they do not shine. Together they compose nearly everything, roughly 95% of the cosmos by mass energy, with about 27% attributed to dark matter and about 68% to dark energy, leaving only a slender fraction for all we can touch and see. The familiar stars, planets, gas, dust, even us, is just the thin foam on the surface of a much deeper ocean. Dark matter is the first veil. It neither emits nor absorbs nor reflects light, making it perfectly invisible to electromagnetic eyes, yet its gravity speaks clearly. Long ago, in the 1930 seconds, Fritz Zwicky noticed galaxies in clusters, moving too fast for the visible mass to hold them. Since then, other lines of evidence, the way galaxy rotation curves remain flat, far from galactic centers, the subtle bending of light, called gravitational lensing, the ripples written into the cosmic microwave background, have all pointed toward the same conclusion. There is more mass than meets the eye. Dark matter forms a kind of cosmic scaffold, a web of invisible structure. Ordinary matter falls into its wells, cools, and gathers. And in those quiet basins, stars ignite, galaxies spin, and clusters slowly assemble. In the early universe, the gentle irregularities, seeded by quantum fluctuations, were amplified by dark matter's pull, shaping the large-scale architecture we observe today. Dark energy is a different whisper, not a weight, but a tendency. In the late 1990 seconds, astronomers studying distant supernovae expected to find the expansion of the universe slowing under gravity's patient hand. Instead, they found acceleration, galaxies drifting apart faster and faster, as though space itself were urged outward by a pressure woven into its fabric. Dark energy appears uniform, not gathering into clumps, and it does not dilute in the ordinary way as the universe grows. Its nature is more mysterious than dark matter's, and it stands awkwardly beside our best theories. It fits neither comfortably within the standard model of particle physics, nor neatly within general relativity's classic picture, and yet its fingerprints are everywhere in the changing pace of cosmic expansion. As space expands under dark energy's influence, it gently alters the timing of everything. How quickly structures form, how temperatures fall, where particles meet to bind into atoms, molecules, clouds, and eventually the stars and galaxies that light the night. To move beyond what the standard model can explain, physicists dream of wider symmetries and deeper structures. One of the most compelling visions carries a quiet, elegant name: supersymmetry, or SUSY. It proposes a hidden balance between the two great families of the microscopic world, fermions, the matter particles, and bosons, the force carriers. In a supersymmetric universe, every known particle has a heavier, as yet unseen partner. Quarks would have squarks. Electrons would have selectrons. The gluon would be mirrored by a gluino. Even gravity's hypothetical quantum messenger, the graviton, would have a gravitino twin. Supersymmetry offers answers to several long-standing riddles. It can ease the hierarchy problem, the question of why the Higgs boson's mass sits so gently at the weak scale, despite quantum corrections that should push it far higher. SUSY can cancel those corrections by pairing bosons and fermions in a delicate arithmetic, keeping the Higgs light without fine-tuning. More than that, supersymmetry provides a natural dark matter candidate. The lightest supersymmetric particles, stable, electrically neutral, and weakly interacting, could drift unseen through galaxies, precisely the kind of particle that would shape rotation curves and bind clusters while remaining dark to our telescopes. If such a particle exists, it might fill the halo of our own galaxy, passing quietly through us in great numbers every second, rarely leaving a trace. And yet, for all its beauty, no superpartners have been confirmed. Accelerators like the Large Hadron Collider, have searched across vast ranges of energy, narrowing the possibilities, pushing the predicted masses for superpartners higher. Each non-detection is a nudge to revise models and look again, more carefully, in different corners of parameter space. Absence is not refutation, but it is a stern teacher. It tells us where the truth does not reside and invites us to keep listening. Beyond supersymmetry, other visions beckon. String theory suggests that the universe's most elementary entities are not point-like particles, but tiny vibrating strings. Different vibration modes sing different particles into existence. The music of the string sets the masses and charges we measure. In this picture, gravity arises naturally, and supersymmetry is not an add-on, but an intrinsic part of the score. String theory also hints at extra dimensions more than the three we move through daily. These additional directions might be curled up, compactified so tightly that we cannot step into them, yet they influence physics in subtle ways. Some ideas, like brain world scenarios, imagine our visible universe as a membrane floating in a higher dimensional space, with gravity wandering more freely than the other forces. The weakness of gravity, compared with electromagnetism or the strong force, might then be a matter of dilution across hidden dimensions rather than a fundamental frailty. There is also the dream of grand unification, where the strong, weak, and electromagnetic forces merge at high energies into a single, elegant interaction described by a larger symmetry. Such theories predict new heavy-gauge bosons that could blur the distinction between quarks and leptons, allowing, in principle, rare transformations that ordinary conditions forbid. None of these heavy messengers have been seen, but their possibility offers a map of where to search in cosmic rays, in proton decay experiments, and in the fine structure of early universe light. All these frameworks, supersymmetry, strings, extra dimensions, grand unification, are ways of reaching beyond the standard model's shoreline toward a broader continent of understanding. They address puzzles the model cannot: gravity's quantum nature, the origin of neutrino masses, the matter-antimatter asymmetry that left our universe filled with matter rather than light alone, and the twin mysteries of dark matter and dark energy that shape the cosmos on its largest scales. Each proposal brings predictions to test, new particles to find, rare decays to measure, delicate symmetries to probe, tiny deviations in the sky's ancient glow to read like script. Experiment remains the compass. Particle accelerators continue to turn energy into revelation, while deep underground detectors wait in quiet stone for the faintest tap of dark matter. Telescopes and surveys map lensing arcs and galaxy clustering, measuring how structure grows under the push and pull of the invisible. Supernovae, baryon acoustic oscillations, and the CMB together trace the geometry and tempo of expansion, constraining dark energy's behavior with ever finer care. The conversation between theory and observation goes on, sometimes confirming, sometimes contradicting, always refining, until what remains is a truth that both equations and sky agree to share. To stand at this frontier is to accept a gentle paradox. The standard model is exquisitely right and undeniably incomplete. It captures the seen world with breathtaking precision and yet leaves most of the universe unaccounted for. Perhaps that is the point. The cosmos has always given just enough light to guide our next steps, keeping the path ahead dim enough to be thrilling. We learn by listening to the hush of neutrinos, to the quiet curvature of starlight around mass, to the subtle pace of expansion. In those whispers, a larger story gathers. So we look beyond the standard model, not out of dissatisfaction, but out of devotion to coherence, to beauty, to the hope that the small and the vast will one day speak the same language. Maybe the answer lies in a symmetry we have not yet imagined, or a field that hums faintly through space, or a dimension curled so tight that only its shadow reaches us. For now, we keep watch, colliders flashing like artificial dawns beneath the earth, detectors listening in the dark, observatories reading the sky's oldest pages. And as we drift toward sleep, it is comforting to remember that mystery is not a failure, but a promise, that the universe we love is larger than our current words for it, and that tomorrow's language may finally let gravity, dark matter, and dark energy sing in the same key as quarks and light. Among the four fundamental forces that weave the universe together, gravity is the quietest and the most patient. It is the weakest of all, yet its reach is infinite. While it whispers faintly at the level of particles, its influence echoes across the cosmos, shaping the universe from its smallest beginnings to its grandest structures. Gravity is the slow sculptor of existence, subtle in strength, yet immense in consequence. In the delicate realm of particle physics, gravity may seem overshadowed by its bolder siblings, the strong and weak nuclear forces, and electromagnetism, but in the wider story of creation, it holds the pen that draws the outline of everything. It is gravity that gathers, folds, and holds the universe's matter together long enough for transformation to begin. Its most intimate role in particle formation is revealed in the birth of stars. In vast clouds of gas and dust adrift in galaxies, gravity begins its ancient ritual. Tiny irregularities in density allow certain regions to pull slightly harder than others. Slowly, invisibly, the cloud contracts. Over thousands, then millions of years, the diffuse mist tightens into knots, growing denser and hotter. When the inward pull becomes irresistible, matter compresses to the point where pressure and temperature soar, and the first fusion reactions ignite. Within these newborn stars, hydrogen nuclei fuse into helium, releasing light and heat, the universe's heartbeat. Gravity's quiet persistence becomes the stage upon which nuclear fire performs. This process, known as stellar nucleosynthesis, forges the elements of diversity: helium to carbon, carbon to oxygen, oxygen to iron, the building blocks of life itself. Every atom in our bodies, every spark of starlight we see, owes its existence to this interplay between the gentle pull of gravity and the fierce release of fusion. Gravity also writes a darker, more enigmatic story, one that unfolds at the edge of black holes. When a massive star exhausts its fuel and can no longer resist its own weight, gravity takes command once more, crushing it beyond comprehension. In these regions of extreme density, space-time folds inward, forming an event horizon from which even light cannot escape. Yet, near this boundary, something remarkable occurs. According to Stephen Hawking's profound insight, quantum fields near the horizon can give rise to pairs of particle and antiparticle from the vacuum itself. One falls inward, lost to the black hole's depth, while the other escapes a soft whisper of Hawking radiation. This phenomenon blurs the line between the cosmic and the quantum, showing that gravity and particle physics are not separate domains, but partners in a subtle conversation. It hints that even emptiness, under the pressure of gravity, can become fertile, capable of birthing real particles from the vacuum's tremble. On a grander scale, gravity's touch extends far beyond the reach of any atom. It is the architect of the cosmic web, the filaments of galaxies and clusters that lace the universe. Across billions of light years, gravity draws matter into vast interconnected structures, leaving behind luminous threads and dark voids. It determines where particles and gases will gather, where stars will form, where galaxies will spiral, and where planets will eventually coalesce. While it is powerless in the intimate tug-of-war within atoms, its cumulative effect over cosmic distances and timescales is irresistible. It sculpts the universe's skeleton, anchoring the formation of matter and defining the rhythm of cosmic evolution. From the birth of the first nuclei to the clustering of galaxies, every act of creation bears the faint signature of gravity's hand. But the story of gravity's role in creation reaches even further back to the first flicker of time itself. At the dawn of the universe, when everything was still compressed into a single radiant breath, a revolutionary idea emerged to explain how the cosmos expanded into being: the theory of inflation. Proposed in the early 1980s by physicists Alan Guth, Andre Linde, and others, inflation suggests that in the tiniest fraction of a second after the Big Bang, the universe underwent a burst of exponential expansion faster than the speed of light, though not violating relativity, for it was space itself that expanded. In that brief instant, the universe's size grew by unimaginable orders of magnitude, stretching the quantum wrinkles of its early self into the vast smoothness we see today. Inflation was not dreamed up from imagination alone. It solved several pressing puzzles in the Big Bang model. One was the horizon problem. How could regions on opposite sides of the sky, separated by billions of light years, be almost the same temperature, when light hasn't had enough time to pass between them since the universe began? Inflation's answer is simple and elegant. Before expansion, those regions were close together, exchanging energy freely. The inflationary surge then pulled them apart far faster than light could travel, freezing their shared temperature into the fabric of the cosmos. Another was the flatness problem. Observations reveal that the universe, on the largest scales, is astonishingly flat, conforming closely to the geometry of Euclidean space. Without inflation, this flatness would require implausibly precise initial conditions. But exponential expansion acts like stretching the surface of a balloon. Any curvature becomes negligible. Inflation smoothed out space itself, explaining why, even today, the cosmos appears geometrically even and balanced. Inflation also offered a breathtaking insight into the origin of structure. The theory predicts that tiny quantum fluctuations in the newborn universe, fleeting variations in density, were stretched by inflation to cosmic scales. These subtle ripples became the seeds from which galaxies and clusters would grow. Gravity amplified them over billions of years, drawing matter toward the slightly denser regions, forming the luminous structures we now see spanning the night sky. Evidence for inflation's truth lies in the faint radiation that still fills the cosmos, the cosmic microwave background, CMB, the afterglow of the Big Bang. Observations from satellites such as COBE, WMAP, and Planck have revealed the CMB's texture, almost perfectly uniform, but not entirely. The tiny variations in its temperature, only 1 part in 100,000, match the patterns inflation predicted. They are the fingerprints of that first expansion, imprinted in light, that has traveled to us for nearly 14 billion years. The uniformity of the CMB once puzzled cosmologists deeply. How could regions so far apart share the same temperature when no signal could have crossed between them in time? Inflation provides the solution. By expanding the universe faster than light could travel, it stretched a once small, thermally connected patch of space into the vast cosmos we now observe. The warmth we measure in the CMB is the echo of that equilibrium, the memory of a smaller, smoother universe stretched to cosmic size. The tiny irregularities that remain, those gentle variations in the CMB's glow, are not imperfections, but origins. They trace the first quantum tremors of creation, magnified by inflation's breath, and later sculpted by gravity into the galaxies, stars, and planets we see today. In this sense, the cosmic microwave background is both a mirror and a memory, a reflection of inflation's power and a record of the earliest interplay between quantum uncertainty and cosmic gravity. Though the theory of inflation has illuminated much, it also deepens the mystery. What triggered that explosive expansion, and what stopped it? Physicists continue to explore possibilities, fields that rolled through energy, landscapes, bubbles within bubbles, multiverses branching beyond our reach. Some models tie inflation to quantum field theory, others to string theory, suggesting that perhaps the same mechanisms that govern particles may have orchestrated the birth of space-time itself. Gravity's story, then, is not just about falling apples or orbiting planets. It is the thread that connects the cosmic and the quantum. It binds dust into stars, stars into galaxies, galaxies into the grand lattice of the universe. It shapes the geometry of space and time, whispers through the vacuum to summon virtual particles, and governs the grand sweep of expansion itself. Though weak among the forces, gravity is the great organizer, the patient hand that turns chaos into form. It began as the faintest tug in the early universe, and has since become the steady pulse of cosmic evolution, drawing together energy and matter to create stars, worlds, and perhaps the awareness that now contemplates them. Every atom, every star, every filament of the cosmic web, all are poems written in the slow language of gravity, the universe's oldest voice. And even now, as we listen to the hum of background radiation, we are still hearing gravity's echo, the echo of creation, finding its shape in the silence after the first light. In the deep logic of the cosmos, balance is everything. For every form of matter, nature has written a reflection, an equal opposite twin known as antimatter. It is a concept both elegant and haunting, for it suggests that creation itself comes with a mirror. Every particle we know, each proton, neutron, electron, has a corresponding antiparticle, identical in mass yet opposite in charge and other subtle quantum properties. The electron's reflection is the positron, a particle of the same weight but bearing a positive charge. The proton's reflection is the antiproton, its charge reversed. Together, matter and antimatter form the yin and yang of the particle world, perfectly balanced, perfectly opposed. The idea first emerged from the mind of Paul Dirac in 1928. Seeking to unite quantum mechanics with special relativity, he wrote equations that allowed for both positive and negative energy states. Rather than dismissing the negative solutions as meaningless, Dirac took them seriously, and in doing so, predicted the existence of new particles, matter's opposites. 4 years later, in 1932, Carl Anderson confirmed this daring prediction when he observed a positron streaking through a cloud chamber, the first known antiparticle. It was as if the universe had nodded in agreement, revealing that symmetry runs deeper than sight. When matter meets its mirror, something extraordinary happens. The two do not coexist. They annihilate each other, vanishing in a burst of pure energy. This annihilation releases high-energy gamma rays, a conversion that perfectly embodies Einstein's famous equation, E equals mc squared mass and energy, as two faces, of the same truth. In a way, every meeting between matter and antimatter is a small act of remembrance, a return to the pure energy from which both were born. Though it sounds like a tale of opposites doomed to mutual destruction, antimatter is far from a mere curiosity. It lives quietly within our own technology and medicine. In positron emission tomography (PET) scans, doctors trace the gamma rays from positron annihilation to create vivid maps of the human body, a process born from cosmic symmetry, now used to heal. Antimatter, once an abstraction of theory, has become a tool of insight and care. Yet its importance stretches far beyond the laboratory or hospital. Antimatter holds one of cosmology's greatest riddles. Why does anything at all remain? According to the most elegant equations, the Big Bang should have produced equal parts matter and antimatter. They should have met, annihilated, and left behind only light. And yet, we exist: galaxies, stars, planets, people, all made of matter. Somewhere, in the earliest moments of time, a tiny imbalance occurred. For every billion pairs that annihilated, one particle of matter survived. That fragile excess became everything. The question is, why? To explore that mystery, scientists create and study antiparticles in the laboratory, recreating the conditions of the early universe in miniature. At facilities like CERN, researchers have learned to form and trap atoms of antihydrogen, the simplest antimatter counterpart to hydrogen, to compare its behavior to its ordinary twin. By studying how antimatter responds to gravity, light, and magnetic fields, they test the very symmetries of nature. If hydrogen and antihydrogen ever differ, even in the faintest way, it could signal new physics beyond the standard model, a clue to why the universe preferred matter over its reflection. At the heart of this mystery lies a phenomenon called CP violation, a small but profound imperfection in the universe's symmetry. The letters C and P stand for charge conjugation and parity inversion. Charge conjugation flips a particle into its antiparticle, reversing its charge. Parity inversion flips the universe's spatial coordinates, like looking in a mirror. If nature were perfectly symmetric, combining both CP should make no difference. The universe should behave identically in both forms. But it doesn't. In rare and delicate processes, this symmetry breaks. Some particles and their antiparticles behave slightly differently when mirrored in charge and space. This asymmetry, though almost imperceptible, may have tipped the balance of existence. If all interactions had obeyed CP symmetry exactly, matter and antimatter would have annihilated completely, leaving only radiation, a quiet, empty universe. But the small violation of symmetry favored matter just enough to survive. In that gentle imperfection lies the reason we are here. Experiments have caught glimpses of CP violation in the decays of neutral kaons and B mesons, particles born in the high-energy interactions of colliders. The differences are minute fractions of a percent, but real. Each confirms that the laws of physics carry a bias, a delicate tilt that lets matter endure. These rare events are among the most subtle triumphs of experimental physics, showing how the vastness of the cosmos can depend on the tiniest deviation from perfect balance. Still, the full picture remains elusive. The known instances of CP violation in particle decays are too small to explain the overwhelming dominance of matter we observe today. Somewhere, perhaps at higher energies or earlier epochs, deeper violations must have occurred, moments when the universe, still fluid and newborn, chose to lean ever so slightly toward matter. That leaning, that faint preference, cascaded through time, leaving behind the worlds and beings we now know. Antimatter and symmetry together tell a story, both mathematical and poetic, a story of duality and difference, of reflections that are almost but not quite the same. They remind us that perfection is not the source of creation, but its undoing. It is the small asymmetry, the almost imperceptible crack in balance that allows existence to unfold. The dance between matter and antimatter, between creation and annihilation, between symmetry and its breaking. This is the rhythm that shaped the universe. From Dirac's equations to the glow of distant gamma rays, from laboratory traps to the faint asymmetry that lets stars form, the lesson is clear. The cosmos was born not in flawless equilibrium, but in a quiet rebellion against it. We live, then, because the universe blinked, because symmetry, for just a heartbeat, was not perfect. And in that heartbeat, everything began. Can we ever truly understand the origin of the universe? It is a question as old as wonder itself, a thought that has lingered in the minds of scientists, philosophers, and poets alike. Each generation peers deeper into the fabric of reality, searching for the first spark, the first breath, the first tremor of being. And yet, no matter how far we reach, there remains a quiet veil, a soft, luminous mystery between us and the absolute beginning. Through the lens of cosmology and particle physics, we have learned to trace the story of creation back billions of years to the moments when energy and matter first took shape. The Big Bang Theory gives us a powerful framework, a narrative of expansion, cooling, and evolution, yet when we look closer to the very first instant, the map dissolves. The laws of physics themselves begin to falter. Temperatures rise beyond meaning. Densities collapse into infinity. Space and time, the very coordinates of existence, tremble and transform. Beyond that horizon, our equations fall silent. This boundary, where knowledge meets mystery, humbles us. It reminds us that science, for all its clarity, is also an act of faith, a belief that the universe is knowable, even if not yet known. Can the finite mind truly grasp the infinite? Can the instruments of experiment and logic touch the origin of existence itself? Some say yes, that the pursuit of understanding is written into our very nature, that curiosity is the heartbeat of consciousness. Others whisper that there are regions forever beyond our reach, truths so vast they can only be felt, not solved. Between these two beliefs, the human spirit oscillates, both restless and reverent. And then comes the question that lies at the center of philosophy and physics alike. What is nothing? In the language of modern physics, nothing is not emptiness. It is not a void where being has ceased. Instead, it is a quantum sea, a restless field, alive with potential. Even in the deepest vacuum, virtual particles flicker in and out of existence, borrowing energy from the void for the briefest of moments before vanishing again. This shimmering uncertainty, called vacuum fluctuation, suggests that emptiness itself is never truly empty. The fabric of space-time hums softly, alive with the possibility of creation. In this view, nothing is not the absence of reality. It is reality waiting to happen. The Big Bang may have emerged from such a quantum tremor, a fluctuation magnified beyond measure. The singularity, that infinitesimal point of boundless density and temperature, marks not only the beginning of space and time, but also the threshold of comprehension. What came before it, if before even has meaning, remains unknowable. Was there truly nothing, or was the universe born from a deeper landscape we cannot yet perceive, a field, a cycle, a quantum rhythm older than time itself? While these questions stretch toward eternity, the pursuit of knowledge continues to yield gifts closer to home. The discoveries born in the world of particle physics have quietly transformed daily life in ways both profound and practical. Out of the study of the smallest things have come tools that heal, connect, and protect us. In medicine, the principles of antimatter have become instruments of care. Positron emission tomography, PET, harnesses the dance of matter and antimatter annihilation to map the living body with extraordinary precision. Magnetic resonance imaging, born from the physics of atomic spin, allows doctors to see inside without harm. From the heart of particle accelerators came the inspiration for radiation therapy, and later proton therapy, a method that can target cancer cells with exquisite accuracy, sparing surrounding tissue. These miracles of precision medicine trace their lineage back to the study of subatomic forces. Beyond the hospital, particle physics has reshaped the modern world. To share data among scientists, engineers at CERN invented the World Wide Web, a creation that transcended the laboratory and wove the entire planet into a single web of knowledge. Particle detectors, once designed to track fleeting traces of subatomic events, have evolved into technologies that serve security screening, environmental monitoring, and even archaeology, detecting the faint echoes of history hidden in stone. Such progress reminds us that even the most abstract quests, the ones aimed at understanding the first seconds of time, can ripple outward into unexpected beauty and utility. The pursuit of fundamental knowledge often sparks interdisciplinary collaboration, where physicists, mathematicians, engineers, and computer scientists converge. From that meeting of minds arises innovation technologies, materials, and methods that shape the century to come. And what of the future? The frontier of particle physics glows with promise. Discoveries in quantum mechanics are laying the groundwork for quantum computing, machines that may one day solve problems beyond the reach of classical logic, decoding complex molecules, simulating entire ecosystems, advancing artificial intelligence, and revolutionizing cryptography. The same quantum principles that describe uncertainty may soon become the foundation of our most powerful technologies. Even the dream of fusion energy, inspired by the same nuclear reactions that power stars, draws directly from the lessons learned in particle accelerators. Within that dream lies the hope of limitless, clean energy, an answer to the challenges of climate change and resource scarcity. In this way, the physics of the very small may yet heal the world of the very large. But the pursuit of power and knowledge always carries shadow as well as light. Particle physics, for all its brilliance, brings with it ethical questions that cannot be ignored. These vast experiments require enormous resources, billions in funding, global cooperation, advanced technology. Some ask whether so much investment in fundamental science is justified when poverty, illness, and inequality persist. The answer is never simple. To seek understanding is to plant seeds for futures unseen. The innovations born of curiosity often bloom decades later in forms no one could predict. There are also concerns of safety, the hypothetical fears of creating black holes, altering the vacuum, or unleashing energies beyond control. Though such scenarios are exceedingly improbable, they serve as reminders of humility. Each experiment must be guided by care, oversight, and responsibility, for the unknown is vast, and reverence for its power is wisdom. Another ethical dimension lies in the use and misuse of discovery. Knowledge itself is neutral, but its application is not. The insights gained from studying the fundamental forces can lead to medicine or weaponry, progress or peril. Scientists and policymakers alike must act as guardians of this knowledge, ensuring that what we uncover serves life rather than harm. Equally vital is the ethics of collaboration. Modern particle physics is inherently global. Thousands of researchers from every continent working as one mind. Yet collaboration raises its own questions. Who owns the data? Who shares the credit? Who gets access when resources are scarce? Upholding fairness and transparency ensures that science remains not the privilege of a few, but the shared endeavor of humanity. In the end, the study of particles of fields, symmetries, and the fabric of the cosmos is also a study of ourselves. It asks what it means to know, to wonder, to seek. It reminds us that knowledge is both gift and responsibility, that every discovery carries the weight of how we choose to use it. As we stand between mystery and understanding, between what is known and what forever lies beyond, one truth remains. The universe invites us to listen not only with instruments and equations, but with imagination and care. Science may never lift the final veil, but it teaches us how to look with humility, with awe, and with love for the endless unfolding that surrounds us. And perhaps that is enough. Not to master the cosmos, but to be part of its conversation, to ask, to wonder, and to let mystery remain, shimmering at the edge of comprehension, where creation still whispers. And now, as our long journey through the birth and breath of the universe draws to a close, the mind begins to quiet, like the stars themselves, settling into their ancient rhythm. We have wandered through the fire of the Big Bang, across the dance of particles and light, through gravity's patient pull and the faint murmur of quantum whispers. We have seen how matter and antimatter mirror one another, how symmetry breaks just enough to let existence bloom. We have touched the boundaries of what can be known and stood before the horizon where mystery begins. Yet even here, at the edge of all discovery, there is no final answer, only a deeper stillness. The universe, vast and unknowable, continues to expand into silence. Every question we ask is like a ripple on that silence, spreading outward, fading gently into the night. Perhaps that is what it means to understand, not to solve the mystery, but to rest within it. Imagine now the great web of galaxies, drifting in space, like glowing dust in a sunbeam that never ends. Between them stretches the quiet fabric of space-time, humming softly with invisible energy. Within that vastness, the smallest particles, quarks, electrons, photons, continue their eternal dance, weaving and unweaving the texture of reality. From that dance came everything: stars, oceans, voices, dreams. And from it too comes this moment, you, listening in the dark, breathing in rhythm with the universe itself. Let the thoughts slow, like planets gliding through their orbits. Let the breath deepen, steady, as the tides pulled by distant moons. The same forces that hold galaxies together also hold the pulse within your chest. You are made of ancient starlight, born from the fusion fires of forgotten suns, carried across billions of years to this single heartbeat. In the end, perhaps the universe's greatest secret is simple. It is not something apart from us. We are the cosmos, learning to see itself. Every thought, every question, every quiet wonder is the universe reflecting on its own beauty. So rest now. Let the galaxy spin. Let gravity cradle you in its patient arms. The stars have no hurry, neither should you. Somewhere beyond the edge of thought, The night folds softly around you, warm, infinite, and kind. You are home among the stars. You always were.